Thank you, Harrison, and thank you all very much for attending my PhD defense called Fast Emulation Bayesian Optimization on Simulation-Based Inference, a modern end-to-end toolkit for particle physics analysis. So my dissertation highlights 7 distinct projects, 3 of which are high-impact projects that I contributed to the CMS collaboration, and 4 of them are separate papers that I conducted independently of CMS. So let me mention that due to time constraint, we will not have time to go over all 7. So we will only go over these 5. And also due to time constraint, we'll only go to moderate depth of these 3 Bolden projects, and time permitting, we'll briefly discuss the other 2. So what is high energy physics? High energy physics, also known as particle physics, is about understanding the fundamental particles of nature and their interactions. So I work on the Large Hadron Collider, or LHC, which is a 27-kilometer circulator accelerator, 100 meters underground, just outside Geneva, Switzerland, and it accelerates and smashes counter-rotating beams of protons. So the goal here is to sort of quote-unquote zoom in on nature's tiniest building blocks and understand their interactions and look for new physics. The LHC is the largest and most energetic particle accelerator ever built, achieving proton-proton collision energies of 13.6 electron volts, center of mass energy. So we start with hydrogen gas, and we strip away its electrons, leaving individual protons. These protons pass through a chain of smaller accelerators that before they're injected into the main LHC ring. We use huge superconducting magnets cooled at 2 degrees Kelvin to bend and focus these beams of protons. And we use radio frequency electric fields to accelerate these protons to 99.99% the speed of light. These counter-rotating beams of protons collide at 4 interaction points, where at each interaction point there exists a different experiment or a different detector. The largest 2 of these experiments are called ATLAS and CMS, and they are general purpose detectors designed to study a wide range of physics. The detectors look like circular concentric cylinders where each layer corresponds to a different subdetector that measure different things such as the particle tracks and energies. We collide about a billion proton-proton collisions per second. And so even using the most cutting-edge technology is impossible to process and save all that information. So we implement what is called a trigger system that reduces these billion collisions into the 1,000 most, only 1,000 collisions that contain the most interesting physics and number that can actually save. We have algorithms that combine the information from all the subdetectors and identify the particles and their properties. And finally, we have petabytes of this data flows from CERN into the worldwide computing grid, such that this data is available for researchers to analyze all over the world. I've been a member of the Compact Muon Solenoid, or CMS experiment, which is a massive global collaboration of over 4,000 people and 240 institutes all around the world, FSU being one of them. So how we work as experimental particle physicists working at CMS is very multifaceted. We are in charge of operating the detectors, calibrating them, aligning them, measuring things such as the detector efficiency and acceptance. We simulate the particle collisions based on theory. We reconstruct the detector signals into these physics objects, and we analyze this data and make statistical inference. So in experimental particle physics, this is the typical pipeline of the steps that must be executed in order to reach at a scientific result that we might hope to publish. And essentially, it's composed of 2 parts that come together. There's the detector side, which supplies the raw data. This data goes through a process called reconstruction, in which algorithms are applied in order to identify these particles and their properties. And then we have another stream in which this data is simulated from some theories, such as the standard model. And the important thing to note is that the simulated data goes through the same processing as the real data. So the simulated data goes through the same reconstruction process as the raw data. And then we have the analysis block, which, given these identified particles and their properties, the outcome of the analysis block is observables, which are quantities that a physicist might predict. And finally, given these observables, we have the inference block. And the goal here is to combine information from the observed data and prediction, and compare them and make some statistical inference here. So I've been privileged to have worked on projects that span this entire experimental particle physics chain. And I will present these projects in red. So on the detector side, I worked on the CMS trigger on something called the L1 prefirer. And also, they're constructing a new detector for CMS called HCal. I worked on the software side of that. On the simulation chain, I worked on the non-perturbative corrections for the inclusive jet cross-section. And on a paper I wrote called Bayesian optimization for PPA tunes. Finally, on the inference block, I wrote a paper called amortized simulation-based frequentist inference for tractable and intractable likelihoods. My dissertation includes two other papers I wrote, one on the simulation chain, one on the inference block. So the standard model is the theory of our best description of the subatomic world, and it combines two theories: the electroweak theory, which describes electromagnetism, which is mediated by the photon, and the weak nuclear force mediated by the W and Z bosons. It combines that with quantum chromodynamics, or QCD, which describes the strong nuclear force mediated by gluons. And these gluons bind quarks into hadrons, where an example of hadron is a proton or neutron. And the strength of QCD is characterized by the coupling parameter alpha strong, or alpha S. So the first project that we'll present is called the non-perturbative corrections for the inclusive jet cross-section. And the first two projects here deal with something called event generators. So let us briefly describe what those are. Monte Carlo event generators use Monte Carlo random sampling to simulate particle collisions or events. And these simulations are informed by theoretical models, such as the standard model of particle physics. And all of these event generators follow a certain number of steps in their simulation chain. So they all start with what is called the Hart process, which is the initial high energy scattering between two partons, one incoming from each hadron. Of course, in this context, we want to simulate what happens when two protons collide. So the first step is modeling the Hart process, which is the initial Hart scattering between the two incoming partons. And this is calculated at some fixed order in the perturbative QCD. Then these high energy partons radiate gluons, and these can radiate further and further. And this causes a stochastic branching cascade called the parton shower. Furthermore, the proton is a complicated thing, and it's composed of many quarks and gluons. So you could have additional parton-parton interactions that did not participate in the Hart scatter, but these partons nevertheless interact with each other. And this is called multiple parton interactions. This is modeled on the first step. Finally, these partons turn into hadrons, which is what you actually observe. And the process by which these partons turn into hadrons is called hadronization. MPI and hadronization are fundamentally non-perturbative effects, so they cannot be described by perturbative QCD. And therefore, they have to rely on phenomenological models to describe them. This first project deals with QCD, and what makes QCD special is that its coupling parameter, alpha S, runs. That is, it gets smaller with increasing energy or momentum transfer, Q. So at high energies, the coupling parameter is small, such that we can apply perturbation theory. And in this regime, we use perturbative QCD to describe partons as free particle states, and this is called asymptotic freedom. As you go down in energy scales or momentum transfer, alpha S grows, such that at some point perturbation theory is no longer valid. And due to quark confinement, hadronization takes over in this regime to form hadrons out of these partons. So in this regime, it is non-perturbative, and we describe hadrons as opposed to quartons. So the first project includes the words jets and cross-section. So let's briefly describe what those are. After a parton is produced, it fragments and turns into hadrons, which is a thing that we actually measure, not individual partons. And the collimated sprays of these particles, mostly hadrons, that we observe in detectors are called jets. And these jets are formed by different clustering algorithms, such as the entity clustering algorithm, which assigns them a jet radius r in that space. The cross-section is an effective area with units such as barns or femtobarns, and it quantifies the probability that a specified final state or process occurs. The inclusive jet cross-section is the cross-section of two incoming partons producing a jet plus x, where x is anything else. So x is inclusive of any final state particle. And this observable provides an important test of various predictions of PCD. Typically, we're not interested in just the cross-section, but how the cross-section is distributed over kinematics. So what we measure is the double differential cross-section, which is the cross-section differentiated per transverse momentum pt and rapidity y. And the theoretical calculation for this double differential cross-section is composed of two parts that are, it's a convolution of two parts. You have the partonic cross-section, which is computed at some fixed order in perturbative QCD. And then this is convolved with the parton distribution functions f, one for each incoming parton, and they give you the probability of observing a parton with momentum fraction x. We integrate over these probabilities and sum over the quark flavors. The way we calculate this double differential cross-section experimentally is we simply count the number of jets that fall within gaze. And we divide it by correction factors like the integrated luminosity or the data size and the vector efficiency, or the product of all the efficiencies. And then we also divide by the inputs. However, at this stage, we cannot compare the theoretical cross-section with the experimental one because there's an extra ingredient that we'll discuss in the next slide. So I contributed to the measurement of the double differential inclusive jet cross-section for 1-2 in CMS. That is for data that is collected between 2015 and 2018. So the jets that we measure in the detector are at what is called the reconstruction level or RICO level. So these RICO jets include the effects of interacting with the trigger and with the detector and the trigger. And we remove these effects by a process called unfolding in order to reach the jets at the particle level. So the green block here represents the experimentally measured and unfolded jet cross-section at the particle level, which is the particle jets. That is the level that includes MPI and hadronization. However, accurate perturbative QCD calculations are made at the parton level, which at this level, this includes parton shower simulation, but it does not include the effects of MPI and hadronization. So in order to bring the predicted cross-sections to the particle level, we multiply these protonic cross section, which includes parton shower, by these non-perturbative directions, C and P, in order to bring it at the particle level, which includes MPI and hydrogenization. Now that the prediction and the observation are at the same level, particle jets level, you can compare them one-to-one. So the definition of these non-perturbative directions is simply the ratio of the cross-section calculated with parton shower plus MPI plus hydrogenization effects divided by the cross-section with only parton shower simulation included. So what this means effectively is that we use an event generator such as Pythia-8, and we generate two parton scattering events, and we generate one sample with MPI and hydrogenization effects turned on, and another sample with MPI and hydrogenization turned off, and we superfit the ratio in each bit. The uncertainties of the cross sections are propagated to the non-perturbative correction factors. And these non-perturbative correction factors approach 1 at high PT of the jet. Therefore, we have to fit it to a function that has that same behavior. And so we pick this function because it approaches constant A0 at high PT. So what we do is that for each rapidity bin, we fit these model parameters of this equation using min-wee, tool called min-wee, by minimizing a chi-squared function like this. What you see here is the relative uncertainties of the NP corrections, and we see that these grow with jet PT. However, since these low PT points will have low uncertainties in the correction factors, they'll be weighted by the uncertainty by 1 over the uncertainty squared. Therefore, the low PT points will actually dominate this spectrum. So even though these high PT points have large uncertainties, they will have negligible effects for the fit. The fit will basically be anchored by these low PT points. Yes, that is indeed this. So what you see here is the results that was handed off to the analysis, and the left column is anti-KT jets with radius parameter equal to 0.4, or AK4 for short. And with the same naming scheme, the right column is AK7 jets. And so for each rapidity bin, we fit this function, and the resulting chi-squared per degrees of freedom, number of degrees of freedom is displayed, and also the best bit values and their uncertainties are displayed. Furthermore, the uncertainties of these best bit parameters is propagated to the model predictions themselves, resulting in these uncertainty values that are shown. And what we see is that these non-perturbative correction factors are nearly flat at 1 across the whole PT range for AK4 jets. And for AK7 jets, these start at about 18% at low PT, and they approach 1 at high PT. And this confirms the previous measurement that was done for this double differential cross-section. And it also turns out to be due to NVR effects, which scale like R squared, therefore it's more dominant for these larger AK7 ejects. One problem is that its jet cross-section falls very steeply with PT, so that very few events will be populated at large PT. And this leads to large uncertainties at high PT bins. However, this region at high PT is the region that we care a lot about, because this is where precision QCD measurements are made. Therefore, we really like to populate that region. So Pythia-8 provides an option for that, which is called bias sampling, which oversamples a process at scale PT hat by this amount, where PT ref and power are parameters that you can manually set in Pythia. And to compensate for this, each event is assigned this bias weight, which is the inverse of that amount. So what you see here is the effect of this bias sampling. On the top row, we don't use bias sampling, and we see that we only populate the spectrum up to like 350 GeV. At the bottom row, using the exact same number of events generated and everything else for fixed held constant, we do use the bias sampling, and we see we populate the spectrum all the way to like 40 eV. Therefore, we really would like to use this bias sampling. However, this produces problems. And the problem deals with these bias weights. And the problem comes because a few rare events can carry extremely large values of these weights, which can dominate the spectrum and cause huge statistical fluctuations in the spectrum. So this effectively means that we need to either generate a lot of events to reach the necessary precision. However, we're noticing that even after generating a huge amount of 10 to the 13 events, we still have large statistical fluctuations caused by these large weights. So the smarter thing to do is simply to remove the events that have these large weights by defining a weight threshold and removing events that have weights greater than that threshold. So by looking at the bias weight equation, I devised this weight cut, and which draws this nice boundary in the log PT of the jet log weight plane. And furthermore, this weight cut or weight threshold is dependent on the PT of the jet alone, because after realizing the PT ref and power are parameters that you can manually set in Pythia, this weight threshold will be a variable weight, so it will change in each event because it will be dependent on the jet PT of that vet. And this turns out to remove only the few rare events that have these very large weights while leaving the rest intact. However, this weight threshold should be chosen in such a way that it only removes these huge, solely pathological weights and leaves the spectrum basically the bulk unchanged. Therefore, it should not cause a big distortion in the PT spectrum. And this plot shows the effect of applying this weight threshold. In the orange spectrum, we weight the jet PT spectrum by the unfiltered weights, and you see that it has a lot of statistical fluctuations. After we apply this weight cut, we weight the jet PT spectrum by these filtered weights, and we get this blue spectrum, which can you see that it's very smooth. These fluctuations disappear. And furthermore, like we mentioned, it should not cause a big distortion to the overall T spectrum. Therefore, to validate that, we have a ratio plot of the unfiltered, the PT spectrum with the unfiltered weights divided by the PT spectrum with the filtered weights. And this ratio is nearly 1 across the PT range, therefore telling us it does not cause a big distortion to the overall PT spectrum. So effectively, what this means is that if we apply this weight cut that I advised, it can reduce the number of events that we are required to generate in order to reach the necessary precision, and also extend the PT spectrum to higher FPC. This is the end of the first subject. Moving on to the second subject is a paper that I wrote called Bayesian Optimization for Pythia Gems. And this was published in Physical Review D. And this paper deals with Pythia, which is the most popular event generators that we use. So as experimental particle physicists, we use this generator on a nearly daily basis, whether directly or indirectly. However, as we mentioned earlier, it relies on phenomenological models for certain aspects of the event generation, for example, for hadronization. Therefore, these models must be fit to experimental data, and the resulting best fit parameters that fit in data is called a tune. And the default values of these parameters of these models in Pythia 8 is the result of the so-called Monash tune. So even if you don't set the values of these parameters in Pythia, which most people don't, the default values that they take is the result of this Monash tune. However, this Monash tune was obtained through manual data-guided adjustments to LEP SLD data. By manual, I mean that the authors made some ad hoc choices of what values these parameters might take based on the theory. And many other tunes have been constructed and are used always at CMS. However, all of these tunes rely on what is called the professor framework, which has other assumptions that lead to other problems. The fundamental challenge of tuning is that these Monte Carlo evaluations are expensive. So we need some way of efficiently tuning these generators. And in this paper, we explore Bayesian optimization, or BayesOpt for short, which is really ideally suited for this kind of tuning problem because of the high computational cost of evaluating the objective function. The objective function is the function that we wish to be minimized. So this paper had two goals. The first goal was to assess investigate whether it is viable, whether BayesOpt is a viable method to use for this tuning problem. And the second goal was to assess whether the tune that we arrived at with this BayesOpt tuning converges to the same point as the monad form. And a key phenomenological model that we considered is the hadronization model, which hadronization again describes the mechanism by which partons turn into hadrons. And in NVIDIA, the hadronization model is the so-called Lund string model. And this model views a quark-antiquark pair as an oscillator subject to this QCD potential, where R is the separation distance between the quark and antiquark. And we see that it has this linear term that grows as you try to separate the quark and antiquark. And the Lund string models use this confining force being a string, such that at some point to separate too far, the string can break, forming two hadrons at two ends. And this model leads to the Lund fragmentation function, which tells you the probability of producing a hadron with electrical momentum Z. And we see this fragmentation function depends on these parameters A and B, which have to be fitted to data somehow. So guided by physics, we tune the 6 most important or consequential parameters in NVIDIA 8. We tune the A and B parameters in the Lund hadronization model, which are the A and B parameters in the previous slide. We also tune 2 suppression factors that deal with quark suppression properties. We tune the alpha S evaluated at mass of the Z boson, which controls the radiation intensity, and we tune the infrared cutoff PT min, below which the emissions are vetoed. And for each of these parameters, we tune over the entire allowable range that these parameters can take in NVIDIA. So we make no assumption whatsoever on what values these parameters might take. We use the LFLEP1 data, which is approximately 30 event-shaped histograms and the event-shaped observables in the form of histograms. And the objective function that we use, O, is a normalized chi-squared-like function summed over all histograms and ends. So X here is a point in parameter space that is a set of values for these 6 parameters. D is the data at that bin. T of X is the outcome of the Monte Carlo generator evaluated at that point X. And delta sigma is the uncertainty of that bin. And we simulate 250,000 events per parameter point to get the necessary precision. So the goal of BayesOpt, just like with any optimization method, is to minimize the objective function. That is to search the domain as efficiently as possible to reach X0, which ideally is the global minimum of the objective function. The fundamental problem is that there's no closed form for O of X. It can only be evaluated at certain points X. And furthermore, as we mentioned earlier, this evaluation is very expensive because of the large number of events that have to be simulated at each point. So BayesOpt reduces this difficult and expensive optimization problem into a sequence of less costly optimizations on a surrogate of O of x called F. The surrogate is less expensive and also has closed form. So we begin by defining a Gaussian process prior for the surrogate F. And we see this Gaussian process prior depends on what is called the mean value function mu and the covariance function k. So we make choices for these. We choose mu equals 0 for the mean function and the Noetherian kernel for the covariance function. Next, we define the likelihood. So our observation y will be the Gaussian will be the surrogate model validated at that point plus some Gaussian noise leading to this likelihood. And as we see, this Gaussian process prior and the likelihood introduce these hyperparameters phi. So these hyperparameters must be tuned or optimized in some way. So to do that, we generate this quasi-random sample with Sobel sampling, it's called DSobel, and we use this data set in Sobel to optimize these hyperparameters phi. Now the Bayes-Opt loop begins. So for each iteration, from 1 to the number of Bayes-Opt iterations that you choose, we begin by computing the posterior functions for mu and sigma, which actually have nice closed forms. Next, we evaluate what is called the expected improvement, or EI, acquisition function from the mu and sigma that were calculated in the previous step. This is the key step in the Bayes-Opt algorithm, which is the algorithm lets us intelligently choose which point to pick next, x star, by maximizing this acquisition function. Next, we evaluate the objective function at this next point, x star, which we calculated on the previous step, and we get this observation, and we simply add this point x star on its observation y to the data set. This ends the Bayes-Opt loop. Finally, our best fit tune, x hat, or our best resulting tune, x hat, is simply the set of parameter points that correspond to the smallest objective function over the entire maze. So to cross-check our results, we use two independent frameworks, gPyTorch and PyTorch, and we proceed in our workflow in 3 steps or 3 stages. In stage 1, we use gPyTorch and we implement the Bayes-Opt algorithm from scratch, and we use the expected improvement acquisition function, and we use this stage to sort of design the Bayes-Opt algorithm and to tune these algorithmic hyperparameters that enter into the Bayes-Opt algorithm itself, which are parameters such as number of Bayes-Opt iterations, number of Sobel points, number of restarts in optimizing the acquisition function, and so on. So we use this stage to sort of on Tory objective functions. So these are meant to mimic the 58 tuning problems without having to use the actual 58 tuning objective, which is expensive. So we use these cheap Tory objective functions to design the algorithm and tune these hyperparameters. Next, in stage 2, we use the algorithm that we designed in the first stage and the algorithmic hyperparameters that we learned from the first stage. And we implement a gPyTorch. We implement Bayes-Opt with gPyTorch and expected improvement, also from scratch, but this time on the actual PTA tuning problem. Finally, to cross-check the result, we use a different tool called PyTorch and a different acquisition function called the Q-noisy expected improvement acquisition function. And this is also on the PTA tuning problem. So what we see here is the result of our gPyTorch implementation on the 58 tuning problem, where each row corresponds to our best fit, our resulting best tune, with a different choice of these algorithmic hyperparameters. And what we see is that our best tune here is the bottom row, which achieves an objective function of 3.7, whereas the Monash point achieves an objective function of 3.2. In other words, gPyTorch doesn't yield a objective function that is lower than the Monash point, so it doesn't beat the Monash point. Next, this table shows two independent implementation of our blowtorch implementation with the Kuhn's expected improvement acquisition function. And we see that in both of these runs, they converge to essentially the same tune as each other, and also close to the previous GPyTorch result. What is more important is that both of these runs achieve objective values that are lower than the Monash point. And therefore, this means that this is a better aggregate description of this lab data set than Monash. So this paper is very significant because not only do we demonstrate that BaseOpt is ideally suited for this kind of generator tuning problem, but we also achieve, across two independent implementations, we achieve a tube that is a better aggregate description of the lab data than the default Monash tuning does not. And however, the physics interpretation does require a bit of care because you have these two competing models, the Barton shower model and the authorization model. And variations in the Barton shower can be compensated by the parameters in the authorization model, leading to these unexpected results. Next subject is a paper that I wrote called Parameterized Simulation-Based Frequentist Inference for Tractable and Intractable Likelihoods. And this was published in Machine Learning, Science, and Technology. So as we know, modern science leans heavily on simulations of physical and stochastic processes. However, these simulators can be kind of viewed like black boxes or a meat grinder if you're more whimsical, because they depend on a lot of these unobserved latent variables called C in the internal mechanism of the simulation chain. So all that you can do really with these simulators is feed it a bunch of parameters data, and at the other end, you can sample data X that has the same structure as the observed data. In other words, you don't have access to the likelihood function, which is a key ingredient in statistical inference. So likelihood-free inference or simulation-based inference try to do statistical inference with simulators without having access to the likelihood function. And of course, the goal is to infer on the true values of the parameters theta, which are unknown. So we were inspired by this recent paper called LF2I, which constructs confidence sets in this context, in this likelihood-free context. And in this paper, they note that a confidence set R for theta can be constructed in two ways. You can either estimate the critical value C, or you can construct this confidence set by estimating the p-value function. So in this paper, we introduce this new algorithm called amortized likelihood-free frequentist inference, or alpha for short, which is this algorithm. And instead of following one of these two options, alpha instead learns the cumulative distribution function of the test statistic with a neural network. And this neural network takes the value of the test statistic evaluated at the data, lambda d, as well as the parameters data as inputs. So in the original paper, they construct their confidence sets for particular data sets, such that if you want to construct a confidence set for a different data set, you would have to retrain your neural network. And we wanted to avoid that. So the way we did that is by including lambda d, which is the test statistic evaluated at the data. And if we include that to the neural network, we're able to construct confidence sets that apply to different data sets. In other words, this amortizes the computational cost of training. We can train this neural network once and reuse the same neural network for different data sets. So here, the learned CDF does double duty. We can use it to construct confidence sets at any desired confidence level. And also, with the same learned CDF, we can check whether they cover the desired confidence level at any point theta in parameter space. That is, whether they have valid coverage. So we apply this alpha algorithm to a classic problem in particle physics called the signal background problem. And in this problem, you observe m events in a background only or control region, and you observe n signal plus background events in the signal plus background region. So your likelihood will be a product of these quasars, a quasan of nu, where nu is the background mean count, which you don't know, and a quasan of u plus nu, where mu is the signal mean count, which is also unknown. So our objective is to make inference on mu and nu simultaneously. So we use this likelihood ratio test statistic, where u hat and nu hat are the maximum likelihood estimates of mu or nu. And we pick this problem particularly in order to demonstrate situations in which standard techniques for constructing confidence sets fail. So standard techniques for constructing confidence sets rely on Wilks theorem, which tells you that this likelihood ratio test statistic asymptotically approaches a chi-squared distribution, such that the computation of critical values will be easy. However, this Wilks theorem relies on certain what are called regularity conditions in order for this approximation to hold. And one of these regularity conditions is that the data should be sufficiently numerous. And we purposely break that condition by choosing low counts for n and n. So this would make DESY, that standard technique for confidence set preparation, invalid, because we just broke that rule. Another regularity condition that Wilks theorem relies on is that the true or NLE value of a parameter must not lie on the boundary of that parameter. And here we purposely allow mu hat to be 0 fraction of the time. And since mu has its boundary between 0 and infinity, mu hat will be on its boundary a fraction of the time. Therefore, we also break a second Wilks theorem regularity condition. So by breaking these conditions, standard techniques of confidence set construction, which everyone else uses, would be invalid in this scenario. But this is not a problem for Alfie. What we see here is the confidence sets for nu and u at different chosen confidence levels using this algorithm. What is more important is that we can use the same learned CDF to check whether our constructed confidence sets have valid coverage. That is, whether their coverage probability here, which is probably that particular set of parameters lie in the constructed confidence sets, are greater or equal to a chosen confidence level. So we check this explicitly for certain choices of confidence levels. So what you see here, the dots are the empirically calculated coverage probabilities at different parameter points. And we see that for each chosen confidence level, this coverage is greater than that chosen confidence level. Therefore, it has valid coverage. And this is satisfied over 500 randomly chosen boundary points. Therefore, we have to empirically show that our algorithm has valid coverage. And furthermore, we apply this problem to two other problems in diverse fields. One is a problem in cosmology called the lambda CDM model, which has a tractable light in it. And another problem in epidemiology, which is called the SIR model. And this problem does not have a tractable light. And what we see is that across all of these examples, alpha yields valid confidence sets. So this is a very important paper, because not only do we introduce an efficient algorithm that constructs confidence sets that have valid coverage, and this applies both for problems that have tractable likelihoods and for problems that don't have tractable likelihoods across diverse examples. And this works even when chi-squared regulator conditions fail. And of course, the code is open source, and I made this website in which you can interactively explore the code, easier for the developers. Let's briefly go over the next two projects. So we don't, at the LHC, we don't collide individual protons, but instead we have we accelerate packets or bunches of protons of each of few protons each, and every time these bunches collide, it's called a bunch crossing. So at the LHC, we produce about 40 million bunch crosses per second. And if we wanted to save every event, that would amount to over 40 terabytes per second. And this is impossible to process and save given even the most cutting edge technology in the world. Therefore, CMS employs what is called a trigger system, which quickly decides which events are worth keeping based on whether or not they contain potentially interesting physics. And in CMS, this trigger system is a two-tier system composed of the level 1 or L1 trigger, which is implemented in the hardware. And this reduces the event rate from 40 million bunch crossing per second, in other words, 40 megahertz, and reduces that to 100 kilohertz. And the events that pass this L1 trigger are passed to the high-level trigger, or HLT. And this is implemented in software, and it further reduces the event rate to around 400 hertz per second. These are the events that we can actually save. One problem that happened in the L1 trigger system, and this happened between 2016 until it was actually recognized and fixed in 2018. And the problem is that at this time, trigger signal mistakenly comes before it should have in the trigger system. Therefore, it can pass a threshold and fire at the previous bunch crossing. And this phenomenon is called pre-firing. So what this means is that the level 1 will accept the previous bunch crossing, whereas the current bunch crossing, which is the intended event, contains the interesting physics, it will be lost. This will not be signal. And this loss of events constitutes an inefficiency. And this is, of course, not accounted for in CMS Monte Carlo simulations. So therefore, this pre-firing inefficiency must be extracted somehow from data and applied to Monte Carlo simulations as correction. So I constructed the pre-firing efficiency or probability maps for the CMS 2017 dataset and triangulation momentum pseudo-rapidity Watt-Hell theta plane for jets and photons, where these are the objects where the pre-firing is most pronounced. And these probability maps were provided centrally to the CMS collaboration, and analyses were able to use them. Furthermore, I repeated this analysis for 2018 dataset, where there everyone was under the impression that his problem had been fully fixed. So we were expecting that there would be no pre-firing, but I actually discovered that there was some residual pre-firing in the 2018 dataset, which nobody had anticipated. And I found the exact runs in which this happened. Well, this was attributed to a defector malfunction in FEL. And after that was confirmed by other groups, these exact runs that I found in which this residual pre-firing happened were removed from the CMS data. So, so my work on L1 pre-firing is very important because these corrections enter a lot of analyses, and they were provided centrally for the CMS for anyone's views. And also for the 2018 dataset, I discovered a large unanticipated residual pre-firing, which was removed from the CMS dataset, which affected the entire collaboration. Moving on, The last project is called the HCal database work. And the high luminosity LHC is a massive upgrade to LHC that is expected to begin operation in 2030. And as part of this update, CMS has been revamping all of its subdetectors. And one of the vector we've been building for this upgrade is a state-of-the-art detector called High Granularity Calorimeter, or HGCal. So HGCal construction is a truly global collaboration that spans many institutes all over the world. And many institutes perform quality assurance tests on various parts that could enter this detector. For example, FSU has been a key site in testing the sensors that will enter this detector. So at each of these sites, a lot of data is produced. And so the CMS HGCal database was developed in order to provide a central repository in order to save all that information from all of the involved HGCal parts, tests, modules, etc., from all of these testing and production sites all over the world. So I worked on several tools that advance the HGCal database infrastructure, and I built these tools that broaden the use of the database, simplify the interaction with the database. So one impediment to the adoption of the database was that the database only accepts information to be formatted in these very finely tuned formatted XML files. They're depending on tables, etc. And our test results, for example, at FSU, for testing these sensors, are outputted in unformatted plain text formats. So in order to upload to the database, we have to convert our unformatted test results to these finely tuned XML formats. So the first tool is a converter that converts these test results into the required XML formats that will actually be accepted by the database. This still required file by file conversion for each of these test results. So my second tool automates the production of these XML files so that now every time we run the analysis on a particular sensing test, these XML files that are compliant with the database, that is, will be ready to upload to the database, are produced automatically. So no file by file conversion will be missed. These will be automatically generated every time you run the analysis. Another impediment to the database was that reading from this database required a full-scale database management system and expert-level SQL and database knowledge. However, we're not database experts or SQL experts. So I developed this tool called Pascal, which is a command line tool that hides this SQL and database schemas behind very simple and short commands. So, for example, if you wanted a simple request to get the IV result of a particular sensor that previously required over 20 plus lines of complicated SQL code, which previously was the only way in which you can read from this database. And with this tool Pascal, you can get that same information with this simple command on the command line. Furthermore, this exports the output of these queries so automatically exports the outputs into CSV files such that you can analyze these data in various ways, and you can explore it later on without rerunning the SQL. So this version was intended as a tutorial version in Python, and a Python module. So it came with interactive Jupyter notebooks and a Docker environment for all the database dependencies. And it also has the command line interface. But to my surprise, this Docker environment was downloaded over 1,300 times. So then I made a new version of Pascal. And this time, this version was optimized to be used on CERN computing clusters. So, and it's only a command line version of Pascal, but it has more commands and on-the-fly plotting. And these commands can be combined with each other to form hundreds of different use cases, depending on what you'd like to do from the database. So my work on the HTTL was very significant because prior to my involvement, nobody was basically using this HTTL database because of its impediments, both in uploading and reading. And after my involvement, people from institutes all over the world have been using segments because of the tools that I built that simplify uploading to the database and reading from the database. So, in summary, I presented 5 flagship projects highlighted in red. These span many different areas in the experimental physics pipeline. My dissertation also includes these 2 additional papers, which we didn't have time to go over. But nevertheless, you can look up any of these papers or you can ask any questions. Thank you all. Okay, let me first say quick words. Huge thanks to by far the best advisor I could have ever asked for, Harrison Fosberg. This could not have been possible without him. Huge thanks to my community members, Professors Yohei, Raina, Murphy, and Meyer Base. And also huge thanks to my parents, especially my family, especially my parents. Thank you.
我3点好，我有一个东西 suggest me. So